Okay, so acid and base reactions are a very common and very important class of chemical reactions. And there are a number of very common acids and bases that we should be already familiar with. But basically, acids have been associated with some pretty characteristic properties. So, for example, they're usually associated with a sour taste. And you can sort of think of lemons as a good example of this, contain acidic compounds like citric acid. They have various well-known reactions with vegetable dyes. So, for example, we can use pH paper or litmus paper to estimate the pH or the acidity or basicity of a solution. Acids have a very characteristic reaction with active metals like magnesium and zinc to produce hydrogen gas. Often these acids are corrosive, and they always react with carbonate salts like baking soda or sodium hydrogen carbonate to produce carbon dioxide. And of course, they react with bases in a neutralization reaction. Some of the common acids that we have encountered or we will encounter are hydrochloric acid, nitric acid, sulfuric acid, and acetic acid. And a characteristic that we should notice right away about the formulas of these acids is that hydrogen is always the first element. So that gives you a good indicator that it is an acid. And of course, the name is an acid. Now, bases are very different. They have sort of the opposite properties. So they're sometimes called alkalis. So, for example, we remember group 1 and group 2 are the alkaline metals and the alkaline earth metals. And that is because when they react with water, they form solutions that are basic, that contain bases. Okay? They are associated with a bitter taste, and there aren't too many common examples of this. I don't recommend you going and tasting the bases present in your chemistry lab, but things like Novocaine at the dentist, you may have gotten a shot from Novocaine and you'll remember that horrible bitter taste. That's because Novocaine is a base. And so that's a characteristic quality of these. Often you'll notice when you've handled a base that your fingers will feel slippery. So if you've touched lye, sodium hydroxide, or like what is in liquid plumber, or bleach, you'll get this slippery feeling, and that's from the base reacting with compounds on your skin cells. It's actually eating away your dead skin cells. These also react with vegetable dyes in a different way than do the acids, and of course they react with acids in a neutralization reaction, which is the topic of today's lesson. Okay, now the common bases all contain hydroxide ions. So we have sodium hydroxide, potassium hydroxide, magnesium hydroxide, and calcium hydroxide, known commonly as hydrated lime, and ammonium hydroxide is another very common one, which is the aqueous form of ammonia. Now, when acids and bases react, they undergo a neutralization reaction. And these neutralization reactions are pretty predictable. Okay, so let's take our simplest example here with very common acid HCl is hydrochloric acid and sodium hydroxide. These react to form water and aqueous sodium chloride. That is, whenever we have an acid and base neutralization reaction, we always form water and some type of salt. Often this salt is aqueous, that it is still soluble, and so it doesn't really participate in the reaction. So in this case, chloride and sodium we would call spectator ions. Okay, so we always form a salt. Now, a simple description of these neutralization reactions is given, or a simple explanation of these neutralization reactions is given by what we call Arrhenius theory. And this is really our simplest description of acid-base reactions, and the one we're going to begin with. So here, the Arrhenius theory defines acids as compounds that ionize in water to produce H plus ions, and thus H is always the first element in the formula, and it will dissociate from the anion in that acid to produce H plus and some anion. Okay, so HCl forms H plus and chloride ions. A base in this theory ionizes in water to produce hydroxide ions. So sodium hydroxide dissociates to form sodium ions and hydroxide ions. And this neutralization reaction always involves H plus combining with OH minus to form water. So one H plus, or 1 mole of H plus, reacts with 1 OH minus, or 1 mole of OH minus, to form 1 mole of water. Okay, now H plus you'll often hear me refer to as protons, because of course the hydrogen atom has just 1 proton in the nucleus, and most of naturally occurring hydrogen is hydrogen 1, so there are no neutrons, so that when we lose this 1 electron to form the H plus ion, we're basically left with an unshielded proton. And so you often hear us describe H plus ion as the proton, and that will become a common term. Okay, so again, for all of these reactions, we have an acid. We have, oh, give me my pen, excuse me. So we have an H plus in an acid like HCl plus NaOH goes to form H2O plus NaCl. So here, our net ionic equation is simply H plus OH minus goes to form water. And this net ionic equation is really important. If we recognize that we're dealing with an acid-base reaction, we always remember that 1 mole of H plus reacts with 1 mole of OH minus to form 1 mole of water. And if we focus on this while we're balancing these equations, the process of balancing becomes very, very simple in these standard acid-base neutralization reactions. Okay, so this will always be our net ionic equation for all acid-base neutralization reactions. So let's do a couple of simple examples here. Okay, these are the ones that we had done as an activity in class. Okay, so here we have HCl, hydrochloric acid, reacts with calcium hydroxide to form water and aqueous calcium chloride. So again, 1 mole of H plus reacts with 1 mole of OH minus to produce 1 mole of water. And we really just want to focus on the water formation here. Okay, so in HCl we have 1 H plus. In calcium hydroxide, we have 2 moles of hydroxide for every 1 mole of calcium. So because we have a 1 to 2 ratio, we need to put a a coefficient of 2 in front of HCl. So now we have 2 H pluses, we have 2 OH minuses in our calcium hydroxide, so we will produce 2 water molecules, or 2 moles of water for every 1 mole of calcium hydroxide, and we're done. Everything else is balanced already. Okay, and this will always be the case with these. If we balance the H plus, OH minuses, and the waters, all of the other elements within our equation will automatically balance themselves. So here's another example. We have H2SO4 with 2 moles of H plus for every 1 mole of sulfuric acid. We have potassium hydroxide with 1 mole of hydroxide, and then we have water and potassium sulfate. Okay, so again, we want to match our H plus and our OH minus. We have 2 H pluses, so we will need 2 OH minuses. So we have 1 mole of sulfuric acid reacts with 2 moles of potassium hydroxide and produces, you guessed it, 2 moles of water and potassium sulfate. So notice again, I didn't need to do anything over here. I simply needed to focus on the H plus and the OH minus. Now let's do one more quick example. So here we've got H2SO4 again, but now we've got aluminum hydroxide. So we have 2 moles of H plus, we have 3 moles of hydroxide. So we need to balance them 1 to 1. So just as when we were forming compounds, we're going to use, in this case, coefficients. So we're looking for the lowest common multiple of 2 and 3. That's going to be 6. And so we're going to put a 2 in front of our aluminum, a 3 in front of our H2SO4. So now we have 6 moles of H plus here, 6 moles of hydroxide. Whoops, excuse me, lost my spot. So we're going to produce 6 moles of water. Oh my goodness. Sorry about that. Almost there. Alright, here we go. Okay, that's going to give us 6 moles of water, and we're done. We don't need to balance anything else. Okay, so we want to focus on H plus. 1 H plus reacts with 1 OH minus to form 1 water. two H pluses, reacts with two OH minus to produce two waters, etc.